The digital design flow, RTL to GDSII. Question: can you describe the standard digital design flow from RTL to GDSII? Answer: the RTL to GDSII route is a comprehensive process that converts a behavioral description of logic into the physical topography of a silicon chip. It can be broken down into several key stages. RTL design and verification. We start by writing the design in an HDL, Verilog, or VHDL, and ensure it functions correctly through simulation and test benches. Logic synthesis. Here, the RTL code is translated into a gate-level netlist using standard cells from a specific technology library. The first optimization for PPA performance, power, area, happens here. Physical design, P and R. This is the assembly stage. We take the netlist, plan the block arrangement, floor plan, place the cells, build the clock network, CTS, and route all the connections, RUTA, physical verification and sign-off. The final check of the design before manufacturing. We use tools to verify the layout against the manufacturer's rules, DRC, and for logical correctness, LVS. Fabrication. The final GDSII file is sent to the fab for photomask creation and chip manufacturing. Question: what are the key input and output files used at each of these stages? Answer: files are the currency in the world of EDA tools. Each tool reads a specific format and generates the next. RTL design. Input: design specifications. Output: RTL code files .v, VHDL. Logic synthesis. Input: RTL code technology libraries .lib, db, design constraints file, SDC. Output: gate level netlist .v, optimized SDC. Physical design, P and R. Input: gate level netlist, SDC, LEF, library exchange format for physical abstractions, PDK process design kit. Output: def, design, exchange format for placement and routing data. Preliminary GDSII, parasitic parameter files, SPEF, DSPF. Physical verification, sign-off. Input: final GDSI, extracted netlist, DRC, LVS rule decks. Output: violation reports, clean sign-off GDSI file. Question: you mentioned SDC, LEF, DEF, and GDSII. Could you explain the difference between them in simple terms? SDC, synopsis design constraints. These are the rules and requirements for the design. It tells the tools how fast the chip must operate, what the clock frequencies are, and the input-output delays. It's like the technical specification for the optimization tools. LEF library, exchange format. This is the abstract physical library. It contains information about the size of standard cells, where their pins, contacts, are located, and which metal layers they use. It does not show the cell's internal schematic. DEF, Design Exchange Format. This is the design itself during the physical implementation process. It contains information about where on the chip each specific cell is located and how all the wires, traces connecting them, are routed. GDSII, Graphic Data Stream 2. This is the final blueprint, ready for manufacturing. It's a binary file containing the exact geometric coordinates of all polygons and layers. This is what goes to the factory. Question: in the physical design stage, what are DRC and LVS? Answer: DRC and LVS are our final quality guardians before manufacturing. DRC, Design Rule Checking, Design Rule Checks. We use a set of rules, DRC Rule Deck, provided by the factory to ensure our layout meets the physical limitations of the process. For example, minimum distance between two wires or minimum transistor width. DRC violations mean the chip likely won't work or will have a low yield. LVS, Layout versus Schematic. Layout versus schematic comparison. The tool reads the schematic from the GDSII file and compares it to the original logical netlist. LVS guarantees that we physically connected everything exactly as intended logically. Question: what is generally the biggest challenge or bottleneck in the design flow today? Answer: today, the main challenges are power management and achieving timing closure at high frequencies. As process nodes shrink, for example, 7 nanometers, 5 nanometers, parasitic effects like crosstalk and IR drop, voltage drop in the power grid, become critical. Physical design requires iterations between placement, routing, and timing analysis to achieve the optimal PPA balance.